I have updated my discussion notes, and just to clarify the updates, so this is just the textbook solution of the practice problem that I went over, and I rewrote it with some more notes. Hopefully this is just easier to view. Okay, and I broke down the more steps. So I included more reasoning as to why we use the equations and how they're derived. Okay, so this is how we found theta for part A, and then this is for part B, A. Now we find the rate of energy loss, but first we need to find the head loss. Okay, and then we find it right here, or watts. Okay, so I just broke it down more steps and listed out the final values all together. So this is good practice for the homework problem 1. Okay, so let me know if you have any questions. And this is the first problem, which we went over, and just more clarity. I included some slides from professors' lectures that would be helpful to refer to. And I added more notes. A student was asking me for 1.2 why m.3 would be negative, and is that because u3 is going to the left? And yes, that's correct. I added more explanation to that in the notes, but here are some good lecture slides that you should refer to from lecture 12. You'll be needing this for question 2 as well, 2.3 actually, and question 1, I think 1.1, and yep, okay, and 1.2. Okay, so this is pretty helpful. Okay, and then we have more notes. So this is for 1.1, the setup, explaining, and then so this is 1.1, 1.1 still, final setup for 1.1, and then we have 1.2. So I added another hint right here because the student was asking me, the wording was confusing for 1.2. What does it mean by, let me go right here. What does it mean to determine the fraction of mass flow along the plate surface? So that means since there is an even split and it splits into 2 streams, you're going to have total mass flow that follows each of those 2 paths after hitting the plate. So it's going to split, and you have m.2 in terms of m.j and m.3 in terms of m.j, basically. And then I show more steps. You will use 2 principles, so the mass conservation and the momentum conservation in the x direction. So we know that the total mass flow entering the control volume must equal the total mass flow leaving. So m.j is equal to the sum of m.2 and m3. But it's not alone enough to determine how much mass flow is distributed. So we know that it adds up to m.j, but it does not tell us the relative proportions or the fractions. So we need the numbers. So we still have to use the momentum conservation. So then we break it down and we use the continuity relationship to delete more terms and simplify. So now we're able to rewrite it like this. Okay. So then you would solve for that on your own. Okay, and then for 2.1, a lot of questions on this problem. So I included some more schematics. I made one, and this is professors. Sorry. So this is there was a lot of questions from students during my office hours um, and discussion on the pressure height differences. They had trouble visualizing it, so hopefully this simplifies it. I hope it's helpful. It's just a oops. It's another viewpoint. Okay, so we have green is the mercury, and it's just flowing and stops right there, and then the rest will be the water flowing through the pipe. So that's why you have to, okay, maybe water. So like this. So that's why we have to, for 2.1, we're going to look at the pressure differences between rho M and rho W because mercury is more dense than water, and I stated that in my notes. So right here, okay, and then I listed what the height differences, the main ones are, and I also included the total height difference, 1, 4, and you can rewrite this when you're solving for question 2, and I even give you more hints right here of how the setup would look like. Okay, so basically what we're finding for 2.1 is P1 minus P2, but that's given already in the problem. Professor already just laid it out for you. And then 2.2, you see the energy per unit mass, and a lot of students were confused what this term meant. The wording was confusing. So if you go to your to Professor's lecture 11, it has the exact same wording right here, and you know that you're going to be using this formula, and these are the units that your answer will be, and you're basically finding GHL, and these are the units. Okay, that's for 2.2. Okay, and 2.3, there was a lot of questions, so I added some more notes as well, but okay, so this is for 2.1 mainly, but it's also helpful for 2.3. Okay, so let me go back. So I already went over this. I crossed this out because it shows you some of the setup, and I want you to solve it on your own, but um, you could ask me to check your homework and I'll see how you're doing. Okay, so these are just more notes on the terms that are involved that you'll be working with. So professor has the schematic for the axial force for 2.3. So you're going to be having that W sine 30 for the weight of the water in the control volume. And we're going to be using Bernoulli's equation. And students were confused about the height differences. So for 2.2 versus 2.1, so for 2.1, yes, we're comparing the pressure differences between the two different fluids, so mercury and water. But for 2.2, we're just looking at the pipe, so we don't need to account for the let me get my schematic. Okay. Oops. Okay, so 2.2 right here. So we are trying to find this for 2.2 and then 2.3. Trying to find FA and then 2.1 P1 minus P2, which will help you solve 2.2. Make sure that your number's right, or else your 2.2 won't be right, obviously. So a student asked me for 2.2. So, okay, let me see. We ignore the height of mercury because we are only analyzing the energy loss in the water flowing inside the pipe. So we are mainly focused on the height difference. Oops. And then you would rewrite that in term that you already found for 2.1 when you're analyzing the height differences. Let me see. Right there. Hint. Okay. So to clarify, 2.2, this is a helpful equation. This is a helpful tip. And then oh, it's right here. Duh. So 2.1, we did need mercury, but it's not needed for 2.2. Okay. And then 2.3, I didn't give too many hints because I already gave so many hints, but basically we'll be using the conservation of momentum in the axial direction this time. So I included notes on the schematic that professor gave. But just to write it out. Oops. And you'll have to account for your terms. So I already listed a couple terms that you'll need. So you have W sine 30, and then P1 minus P2. Oops. P1A, P2A. And then you'll need to find FA. Okay. So you'll need to basically create a balance equal to 0 using all those terms. And your answer should be of course in newtons. Oops. And don't have a negative answer. Your answer will be opposite to flow direction. Okay, so let me know if you have any other questions. I just felt bad for the students who didn't have a discussion yesterday, and then I've been sick, so hopefully I sound better right now. But I could still include the discussion that I recorded this morning during the discussion, just in case anyone feels like they missed out and they want to see what I did, even if I didn't sound great. I could include that for after this video right now, just to compare and contrast the differences of the notes I added. And I made a typo mistake when I was because the student asked a good question on what our answer would look like for each part for question 2. And I wrote this wrong for 2.2. I'm sorry. I wrote this, but that was a mistake. I meant to put L. Okay. Okay, hope that helped. Let me know if you have any other questions. And my notes are posted already besides this, but this is pretty basic. The video hopefully helped more, so I don't need to repost this. Okay. Have a good night. Okay, so I thought this would be a really good practice problem because it looks really identical to the first problem. And I'll ask Professor if this one is fine. But it should be fine. It's really similar. And it's a pretty good problem. So we have a homogeneous jet. 2 water jets collide to form one homogeneous jet. And we have to determine the speed, direction, theta of the combined jet. Determine the loss of a fluid particle flowing from point 1 to 3 and from 2 to 3. Gravity is negligible, and that's from the textbook. Okay. So 5.3.38. Okay, so I'll include a copy of the schematic as I go on. Okay, so I'm just listing out the values, and then
What's this question asking? Oh, sorry.
that's okay. Okay. Okay, so since we need to determine the speed and direction, first we start off with the conservation of mass continuity equation. So for steady and compressible flow, we have m.1 plus m.2 equals m.3, and then it just gives us, we can rewrite m dot into the mass flow rate formula, which is rho AV, and then A is pi d squared over 4, and we can now rewrite it and cancel out the rows. Okay. Crop this. Okay. So then we're able to find V3, which is the goal. Highlighting. Okay, then we get 4.29 using this equation. And we're using the same cross-sectional area because it's the same shape throughout, which was A equals pi d squared over 4. So these are formulas you've already seen. We're just
combining them into the continuity concept. Okay, so now that we've found V3, which was part of part A, we also still need to find the direction for part A of the combined gym. So now we have to do more conservation of momentum in X and Y directions. So in the X direction, we have this balance right here. Bring this down. Okay, any questions? Okay, so then we also have the Y direction balanced, and this is good prep for the homework. I can post another practice problem if you need more practice. And then we use this, the tangent relationship, to use both those equations, and we find theta. Okay, and then we find it to be 17.2 degrees. And that was for part A. Determine the speed, and direction of the combined jet. Okay, any questions? Okay, so then we move on. Let me bring this down. Okay, so now we're using Bernoulli's equation to find the energy loss, because for part B, that's what it's asking for. Okay. So now HL is the energy loss, so head loss. Okay, so then we isolate and find that it's 1.9 meters. And now we need use that to determine the actual energy loss. So okay, then we rewrite. I can show more steps. I can maybe add more steps to how we found this formula, yeah? Okay. Okay. Then we find energy loss. Let me see. It's too light. Is 558 newtons meters per second. Hi, welcome. Okay, and then I listed out all the values we found from this problem, and I could go over it again. So we can rewrite this aka as watts. That's why it's written like that. Okay, so we used the head loss that we found over here to find the actual energy loss. So you don't just stop right here if the problem is asking for the loss of the fluid particle flowing. So that's why we had to get the rate of energy loss. And there's another solution, but I just listed it out more right here. So just to clarify, this is actually the right way to do it. So this is written a little weird, so that's why I rewrote it, but this is another way to look at it if you want. And I could post this. This is the textbook's way of doing it. So to determine the loss of available energy associated with the flow through this control volume, we apply the energy equation and the conservation of mass and assume Q dot is 0. I can add this step actually. And that lets you get the rate of available energy loss on the left hand side. Okay. So I can maybe show more derivation steps. Okay, so I can walk through the problem again. So any questions? Okay, so this is just to prep for the homework. So just to review, so we had this very similar problem to homework problem 1, and the two water jets collide, form one homogeneous jet, and we have to determine the speed and direction of the combined jet, and then we have to determine the loss for a fluid particle flowing from 1 to 3, from 2 to 3, and gravity is negligible. So the main concepts over here, using conservation of mass, aka the continuity equation, conservation of momentum in both x and y directions, which is seen in problem 1 of the homework 7, and then Bernoulli's equation for energy loss, which can be rewritten lots of ways, so get used to practicing that. Okay? And then I listed out the values. So jet 1 and jet 2 have slightly different velocities. So, and then the resultant jet is d equals 0.12 meters, and gravity is negligible. And professor's assumptions can also be written right here. I think it was water is incompressible or something, or we already have gravity is negligible, and then incompressible fluid, I think. Oh, I read it over here. Where is it? Yeah, okay, great. Okay. So then we apply the continuity equation to find the velocity v3, because we're given v2 and v1. So then, and we're using the same cross-sectional area for all 3 points because it's the same shape throughout, just 3 different points. And so then that allows us to isolate rho, cancel out rho, and then we find v3 is 4.29 meters per second. And this is problem 5.3.38 in the textbook. And I'll post this after class. Okay, so then that led us to solve the direction of the combined jet. So we need to consider the conservation of momentum in x and y directions. So then in the x direction we have this balanced out equation, and in the y direction we have this equation. So we combine using the tangential relationship to get theta in using those equations. So So then we find that theta is 17.2 degrees. And then we have to solve part B, which is the loss for the fluid particle flowing from 1 to 3 and then from 2 to 3. So first we start off with Bernoulli's equation and we find the head loss, but we still need to find the rate of energy loss. So we don't stop there, but this is the setup. And then we keep going to find the rate, and we get 558 watts, or Newton meters per second. And I can show more steps to derive those equations and add it to my notes when I post it. Any questions? Okay, I'm going to move on to the hints for the homework. Okay, so I showed on Friday a couple hints, but I added better notes now. So we have problem 1, which is very similar to the practice problem I just showed. Hopefully you can see that, the similarities. So we have jet velocity 40 meters per second this time, and the horizontal circular jet of air strikes a stationary flat plate, and it shows in the figure. So the jet diameter is 30 millimeters, and the air velocity magnitude remains constant, which is important to note. As the air flows over the plate surface in the direction shown, the density of air is 1.2 kilograms per meters cubed, and we can ignore the weight of the air. So I added that to our assumptions. And we have to determine the magnitude of Fa, which is the anchoring force required to hold the plate stationary, and then determine the fraction of mass flow along the plate surface in each of the 2 directions, and also determine Fa required to hold the plate to move to the right at a constant speed of 10 meters per second. So I gave the control volume schematic that professor has to help start, and then we solved 1.1 because a couple of students already made some connecting concepts, so they had finished half of it. So we have our control volume, and I added explanation. Let me just put it side by side, maybe. Okay, there we go. So this is just to show more clarity, and the inlet is before impact, and the control volume surrounds a section of air, the air jet just before and after it impacts the plate. So the air enters the control volume added as a jet moving with velocity 40 meters per second, and the jet is inclined at 30 degrees to the horizontal. The mass flow rate at the inlet is m.j, we're calling it. So the outlet is after impact, and this is where the air splits symmetrically into 2 streams. One stream moving 90 degrees upward, perpendicular to the plate. The other stream moves along the plate. And because of the symmetric split, both outgoing streams have the same velocity magnitude as the inlet velocity. And that's important to note. And a student asked me why it's symmetric. How do we know it's symmetric? Well, it's given in the schematic. That's why it's showing the 90 degrees right here. So it's at an angle of 30 degrees, but it's being evenly split, which is shown with the 90 degrees right there. So that means that it does not contribute any y direction momentum after impact. Therefore, the y component of momentum is fully stopped by the plate, meaning that the plate must exert a force to counteract the momential loss in the y direction. And I'll show what that means within the equation. So initially the air has the vertical velocity component, uj sine 30 degrees. But after impact, there's no outgoing velocity in the y direction. So we have this setup, linear momentum equation in the y direction. So that means that this will cancel out, and you're just left with, it says right here too, u out equals 0, which we were just talking about. Since the outgoing airstream split symmetrically, all the momentum in the y direction is stopped. So then we're just left with FA equals m dot j uj sine theta. So this was pretty simple. Let me know if you have any questions for 1.1. And a student had a question about the area. So you can rewrite it differently. So radius is just d over 2. And that means that because it was 30 millimeters, where is it? Yeah, 30 millimeters. So then we can rewrite r as 0.015. If you see professor's solution and get confused, that's why. So it would be pi r squared or pi d over 2 squared. Okay. Okay, any questions before I continue? Okay, so for 1.2, okay, a little hint. So the incoming jet has an x component of velocity before impact. After impact, the air splits into two streams, so you need to consider how their velocities affect momentum balance. Since there are no external forces in the x direction, momentum must be conserved in that direction, and the total mass entering the system must equal the total mass flow leaving the system. So, and then you also have the continuity concept where it's given that velocity magnitude remains constant. So that means that u2 equals u3 equals uj. So you're going to need that for 1.2. Okay, any questions? Okay, I've given a lot of hints for problem 1, so I'm moving on to problem 2.
Really quick, can I ask for 1.2, what is implied by the fraction of mass flow? Are we going to be comparing two things and taking like a ratio, so to speak? I was a little confused by the wording itself.
Yeah, okay. Let me see how much I can share. Basically, you're finding m dot 2 and then m dot 3. So that's equal to blank m dot j. That's basically it. So like it's a portion of m dot j, so it's like a fraction of it. That's it. Yeah. So you use the magnitude, the air velocity magnitude remains constant. That's a big tip. And then momentum conservation in the x direction. So then use the mass conservation concept to set up your equation, which is kind of what I gave. So yeah. Oh, it's over here. Any other questions? Okay. So for problem 2, I had given the schematic. And I stated the assumptions: incompressible, steady state, constant G. And so just to this bigger. Okay. Okay, so we need to determine the pressure difference, P1 minus P2, and it tells you pretty straight up, so we don't have to worry about any confusing wording for that part. And gives you the density for mercury, and we have the inclined pipe right here, and it's in 2 sections, which is important to note. So it has a couple heights, and you're going to have to apply those height differences to find the pressure differences, which is important. So to find the pressure difference between sections 1 and 2, we have to use the hydrostatic pressure equation by analyzing the height differences in water and mercury columns. So the pressure at point 4 is the bottom of the mercury column. And it's the same on both sides of the manometer, which we can use to relate the pressures at point 3 inside the pipe and point 2. And this will give us our height differences. So these are the total height difference equation. So all the contributions from multiple sections. It's basically how one way to look at it. So that's going to be helpful. When you apply your equations. Okay? And so height 1, 2 is the vertical height difference between sections 1 and 2 due to the pipe inclination, and height H34 is the height of the mercury column, H23 is the height difference of the other section in the system. Okay? And then another important note is that the pressure drop due to the mercury column is scaled by rho m minus rho w, and the pressure drop due to the water column is proportional to rho w. And because mercury is much denser than water, that's why we have rho m minus rho w for this relation. Okay. Any questions? Okay. So that's for 2.1. And I can refer back to the schematic that I have right here. So okay. So for 2.2, let me just we're applying Bernoulli's equation. Oops. Okay, so we're given in the problem that U1 equals U2 since for 2.3. See. Okay, so since with our assumptions, we assume that incompressible in its steady state constant G. So then if we, for 2.2, we have the Bernoulli equation, and we use the continuity relationship that U1 equals U2. Okay, so we continue using that in 2.3 with the conservation of momentum in the axial direction, but important to note for number 2. Sorry. So then going back, so I pretty much gave some of the equation, but I wasn't supposed to. Let me see. I don't think I was supposed to. I was gonna exit this out. Oh, wait, no. Let me see. Okay. No, it's too late. Okay. Hopefully you can figure that out. But so we're able to cancel out terms just based on this continuity relationship where U1 equals U2. So make sure you apply that. And then we are finding for 2.1 P1 minus P2. And then 2.2, we're finding basically GH2, which is the loss between sections 1 and 2 in the general form energy per unit mass. Okay. Okay. And then 2.3, we determine FA. But going back to the schematic, so just some notes on the schematic. Let me see. Okay, so the forces are acting on the control volume of water flowing through the inclined plane. Let me just get the problem again. Okay. Put it side by side. Okay. Okay, so we have to determine the net axial force exerted by the pipe on the water. So we have to follow the momentum conservation in the axial direction. So P1A is the force exerted by the pressure at section 1, and then P2A is the force exerted by pressure at section 2. So the axial component of the weight would be W sine 30 because it's at the inclined angle right here. Okay? And that's what the schematic is trying to show. I can move it. Let's see. So this W would be this component, so. Okay, so this is the normal force. And then FA is what we'll be finding for 2.3. Okay, which is the force exerted by the pipe wall on the water. The force exerted by the pipe on the fluid to keep the system in equilibrium. And the force is opposite to the flow direction. So the pipe is resisting the motion of the water. So this is just visualizing the axial momentum balance and the key forces that are happening. And we're following Newton's second law for momentum to determine the required force exerted by the pipe wall on the water. Okay? So my notes. Any part you want me to go back to? Yeah.
Yeah, can you go back to 1.2?
Okay.
Yeah, so when we're finding the fraction, we have to know that the velocities are the same, right?
Yeah. So U2 equals U3 equals UJ, because it's given that the velocity remains constant. Okay. So then you're able to say, oops. I'll make this smaller. Okay, it's way better. Does that make sense?
Yeah.
Okay.
And also, if you go over to the last one again and explain so we have to set the conservation of mass formula only.
For which one?
2.3 as well.
1.3?
2.3.
2.3? Oh. Yeah, for the axial direction.
So it's going to be like L dot, right? L dot in, L dot minus L dot out. Minus the force. And that's it.
Yeah, you don't have to use L dot. That's just professor's notation. You can also use the common notation, which is what that's why I listed it this time, not as L dot, so you don't get confused like this. The sum, as long as you have the M dot U, and then you relate it to the typical rho AV, you're fine. That's just professor's way of writing the linear momentum. I just didn't want to confuse you. So I wrote it a little different, but if you like the L dot, I could keep that.
I guess, but if you use the L dot, then the velocity is squared, right? In that case, because since in mu, it's rho av, and then you also have the u, which is basically the v in that case. Right?
Yes. Yeah. Any other questions? Okay, if you want me to go back to a part before I post the notes or anything you want me to add to the notes before I post. I have office hours today, 12:30. If you want me to check your homework, I can. Or any other questions, so let me know or email me. Okay. Well, if you don't want me to go back to a part, yeah.
I was just wondering for number 2, what will we, like, if we're given that on the exam, would we be given the the density of mercury, or would we have to be, because in the problem, does it state it, or, because I'm looking at it and I'm not too sure.
Yeah.
It's the density of mercury, so would we, when we were finding head loss,
Uh-huh.
I'm just not too sure, how do we keep it in, do we keep it in kilopascals, or do we convert it to pascals?
Mm. Oh, I see. So the units work out to, because you're trying to find the force for 2.3, so you'll be getting newtons, but it's already in the form, so you don't have to do too much rearranging. The main focus is, because for 2.2, let me rephrase this. So I'll write it down. So for 2.1, yes, it will be in pascals. And then, but you're not rearranging too much of the units. It just happens to work out like that as you calculate, you know what I mean? And then 2.2, you're finding the energy per unit mass. So that means that your units are going to be meters squared per second squared.